Okay. Um, there's a when after the seniors are gone, there'll be those 2 weeks of AP week. The AP week is 2 weeks of AP. Yeah. We're gonna have essentially project stuff in class, but it's gonna be project about. Yes, we have a million projects. They're gonna be. I know. These are gonna be about your big projects will have been done by that time. Okay. Your big projects are due end of next week.
No, they're due the end of May 6th.
Yeah.
You said May 6th.
You said they're due. You said they were due May 6, 2099. You said they weren't due so long.
Yeah.
You said May 6th, so we're not.
You never specified.
Stay put. Okay. Shh. Okay. So, that's right. May 6th. Shh. I don't. Kiddo, I don't know. You're gonna have to look around. I'm in the middle of class. Guys, quiet. All right. So May 6th. So everything's due that day. I'm gonna have you guys do some projects based on some of the things we've done. You're gonna do a mobile, and maybe that or something else. I'm gonna make some decisions here pretty soon about what you're gonna do. I want to talk briefly. I'm going to do a very quick example about how to do the mobile. All right. So let's talk about how. Does everyone know what a mobile is? Does anyone know who the artist is who designed this?
Alexander Calder.
There you go. Oh, there it is. Sorry. That was silly. Okay. So, shh, quiet, guys. Okay, silence. About?
Oh, that was a major eye roll there.
About? No.
Well, are we going to get a project?
Yes, you're gonna have a project this week. Yes. Okay. So when I think about the seesaw problem, right? We think about the seesaw problem. Can I have that? Thank you. We know we had the forces here, right? F1, F2, right? Hello? And we had a pivot point here, correct? Okay. Typically, I've been giving you lengths, but this time I'm going to make you solve. You're going to have to solve for lengths, okay? So when you think about a mobile, okay, where I have some sort of object, you're going to design this in SolidWorks, and you're going to laser cut your parts. SolidWorks, Guys, I'm getting through this, and there's not much time. There's a lot to get through. I'm going forward whether you listen to me or not. Simple as that. You're responsible for this, period. The weight comes from the amount of material you have hanging, right? How do you calculate the weight of something? Not with a scale. How do you calculate it? How could you? Okay, that's the weight, but okay. So you need to have the mass, right? Okay, how do you find the mass?
Times the gravity.
No. Well, how do you find the mass of an object? Let's say you knew the shape. You're going to design it, right? If I had a rectangle, there you go. If I knew the area, Kaylee, quiet please. If I knew the area and I knew the height times area is going to give me my volume, times my density is going to give me my mass, right? I'm sorry? You're correct. And you have material, and you're going to mass out. You're going to mass out the material you have and look at a piece of material that you know the right amount. You're going to figure out the density, and then you're going to determine based on. And the nice thing about SolidWorks is if you draw something very amorphous shaped like this, it will calculate the area for you. Okay, and then you know the thickness, and therefore you know the density. You can calculate the mass. Okay, does that make sense? All right. So you're going to have two forces. You're going to have force 1 and force 2. Okay? Force 2 is going to be much bigger than force 1 set. Okay? And we're going to hang this with a little rope. How do I know where this rope is going to be? Depending on the forces, right? It's going to be where it's going to be balanced out, right? So if I knew the length, and you're going to pick a length. You're going to pick a length for your beam, and you're going to say, hey, there's another length from here to here, which is question mark. Okay? Or X. So if we do this, how do we balance this out? How do we do the calculations, guys? How would I solve? If I knew my forces and I knew my lengths, or knew that one length, what would I do? How can I find this length right there? Some of the what? Some of the torques, right? Some of the torques, and if I call this point A, point B, point C, what would be the most logical place to put your sum of the torques around? A would be a good place. A, or actually B is a really good place. B is a good place. So some of the torques around B, around any point, is the torque from A plus the torque from B plus the torque, I'm sorry. I'm going to call this force of the rope. So torque of force 1, torque of my force rope, and the torque of force 2, right? So my torque 1 is going to be force 1 times what? Length from B to A, right? Plus force RP times the length from B to B, plus the force 2 times the length what? B to C. Right? You guys see that?
Yes.
Okay. Let's say F1 equaled 5 newtons, F2 equaled 7 newtons. Okay? And my L was 13 meters. Or let's make it more real, 1.3 meters. Okay? 1.3 meters. So force 1 is how much? What's F1? What's F1, guys? 5 newtons? Negative 5 newtons. What's LBA? LBA, we don't know. We're going to call it X, right? Or actually negative X, because it's the other direction, right? Okay? Or actually call it X, whatever you want to call it. Call it X. The negative will come out. Call it X. Plus FRP times LBB. What's LBB? 0. From the L of, because we don't know the FRP unless we do the sum of the Y's. Well, we could do that. We'll call that 0 plus F2, which is what? Negative 7 newtons times what? No, the whole length is 1.3. What's the length from B to C? I'm sorry. This is L, B to C. B to C. The length is L. The whole length is L. What's LB to C equal? 1.3 minus X. You see that? And that's all going to equal what if I'm balanced? Okay? So it's negative 5x minus 7 times 1.3, which is 9.1, minus or plus 7x equals 0, right? Okay, so that means negative 9.1. Oops, excuse me, I'll take that back. That means 2x equals 9.1 meters. Or 9.1. So x equals 9.1 divided by 2, 4.55 meters. That's my distance x to where the rope needs to be to balance. Does that make sense? Are you writing that down? Because you're going to need that next week. Okay, beautiful. All right, so you need to know how to do that. This will be another, you're going to have to do, the project that you're going to turn in is going to include the calculations. Okay? This is being recorded, yes.
Yes.
Okay. So here's the thing, though. Two units in one length is pretty simple to do. Very trivial, or relatively trivial. What becomes non-trivial is when you've got this, and Trip and Dave pair up with Colby and Netta, right? And so now you've got.
Dave. You're so neat. You call him so many different things.
What do I call him?
David Dentino.
All right. Shh. Okay, so quiet. Shh. So let's say this guy. Let's say this is Dentino and Trip. Okay? And then let's say that this, okay, is Colby and Netta, right? Okay? But then there's gonna have to be shh. Oops. Some position here. Actually, come back. Okay, right? So there's that now system. You have to figure out where the balance is for that. Balance point, right? But then this is going to be over here, right? And now I've got to get this to balance out to this guy. Okay? So all of a sudden, guys, this becomes non-trivial very quickly because you're going to make one mobile for the entire class.
So we're all in this together.
You're all in this together. Now you can decide to make it any way you like. Okay? If you want to make it sort of Alexander Calder-ish, okay? Okay? So let's say you do an item like this, okay? And let's say you had some sort of let me come back here. Right? Okay. And you had another item. Right? Like this. Okay? Shh. Remember, guys, just like the bent beam, it's like doing it like this, where you've got your force here and your force here, where this is my length from here to here and here to here. You guys, does it make sense? Okay. The other thing you have to worry about is the mass of the material. This bar is going to have some mass, isn't it? Okay? So let's go back and let's do the next. Let's come back here for a second. Okay? If I come back to this, let's think about this for a second. Let's say the bar has a mass. Okay? If I have my ruler, and let's say the ruler is uniform density, where is its weight?
In the middle.
In the middle. It's as if it's a point source at the middle, going down. Does that make sense? So there is the weight of the ruler, or this bar, is right here, FG, where this distance is what? L over 2. Does that make sense? So you have, in addition, you have another torque. You have another torque you're missing. Plus torque of my center of gravity or of my ruler. Does that make sense? And you've got to add that in. Guys, all it is just keep adding stuff up, right? And you can determine, because you're going to decide what your bars are. You have wire, you can use PVC pipe, you can cut pieces from wood, whatever you want to do to make that mobile. Does that make sense? But you're going to have to show the calculations as a class. It's going to be for a grade, to get that done. Yes, sir.
How many pieces is it going to be?
It's going to be one per person. One per person.
One piece or one?
One piece per person.
Okay.
So it's going to be 20 pieces.
You're not like with the group?
So yeah. So here's the deal. So if Kaylee and Chris are a group, Kaylee's going to design a part, Chris is going to design a part, and Kaylee and Chris are going to design this piece. Then that group is going to work with these guys, and they're going to put that together and make the other section.
But are there?
But you can, huh?
But you said so we each make one little part.
Yeah, each of you is making a little piece,
Okay.
but then you have to work together to figure out how to balance it.
Okay. Do we have to sign our name on our piece?
Yeah, you can do whatever you want on it, okay?
Everyone
But
one?
if you're doing this, you're doing something that's going to look. You have to think about this as a class. If you want a uniform look, you have to decide what you want to do and sort of vote on it and figure out what general form you want. And then you can all sort of do some similar pieces. And then can sort of go together. So you might have to have some, this is going to be very stereotypical and I apologize, but who's your most artistic designer person in the class? Sam will be gone by then.
No, not artistic.
Oh wait.
He's not artistic. Yeah.
Unless he wants to go back to hell. Who's my next most? Oh no. Then you guys.
Chris Tisler.
Chris Tisler. So Chris will be in charge of the overall design and generally overseeing all of your designs to make sure they look similar.
Wait, they have to look similar?
Well, if you have to decide, do you want to, let me finish. You have to decide if you want a uniform design, okay? Make sense?
Uniform. I don't like the big four.
We're doing squares and circles and triangles.
That's fine. That's perfectly fine. That's perfectly fine. These will hang up in here for the rest of this year and next year. Huh? I know they're being hung up so people can see. They're gonna be around campus. We're gonna install them around campus. Yes, during AP weeks. During AP week, yes. Yes, this is gonna be during AP weeks. Quiet. Shh. Quiet. You're gonna have an individual grade. So you're gonna all have a grade that it's gonna be a completion grade that you have to show me all of your work. You're gonna turn in. I'm gonna figure out how this. You might actually I might have you put the calculations and laser some calculations on your piece. Yeah. All right. Shh. Quiet.
So are we learning all the air resistance stuff that you said we were going to do during AP? You said we were going to be learning like all new material.
We are. We're learning stuff now. The next 2 weeks we're learning, and then those 2 weeks, I'm showing you this now.
Well, we only have a week and then you're having.
No, we have a week and a half. We have this week and next week. We have this week and next week. 2 weeks. Quiet. Not gonna say it again. We have this week and next week to learn some material, which we're doing now. Okay. I'm prepping you so that during the week of the AP weeks, you have the projects you're going to do.
Okay.
This is going to be one of probably 2 projects
Okay.
that you will be open to do during that time.
So are these like our last grades? We're not going to have another test then?
I will have probably an assessment at the end of next week, okay, on the new material. Okay, and then it'll be on the final. All right, shh, quiet. Okay, next thing I want you guys to do is this. We're going to do one more friction problem, the one thing that I skipped over, okay? All right. The one thing I want to talk about is we've all done friction when your object is sitting flat, right? The issue is what happens when your object is not sitting flat, okay? All right, so it is slanted. That's the problem. All right, so okay, so let's assume that we've got an object, quiet, and the object is sitting on the platform at a slight angle, okay? All right, now let's assume, guys, please be quiet. You really need to. You're going to be responsible for this either way. Okay. All right. Let's assume that this object sitting here on the platform, we have an angle theta. Okay. All right. Let's say I have a rope pulling. Oops. I have a rope pulling up on my object this direction. Okay. And let's hold the rope off for a minute. Let's hold the rope off for a minute. All right, we'll put the rope in. Your honors to do the rope. Fine. All right, quiet. Ah.
Mr. It's funny when I go back to the recordings and see how much complaining you do.
I know.
It's hilarious.
It's not funny. You've wasted half the semester. You waste half the semester. Okay, so let's draw the forces. Let's draw the forces on the object. Let's draw the force. What is the first force you know you have? Gravity. So it's acting from the center of gravity down. This is force of gravity. What else do I have? Normal force. Which direction does a normal force go? Perpendicular. Okay, to. You did get it right. To the surface. So it goes like this. Normal. Okay? What's my other force that I have? Friction. Now, what direction is friction going? Upward, yes. Upward to the right because it's going to be, the friction's always parallel to the surface of friction's at, right? Okay. No, it's friction. Friction, okay? Because gravity's trying to pull it down. What's the problem with this problem right now? What's stopping us from completing the problem? The angle of what?
Of the friction.
Here's the thing. We've got three forces. Two of them are perpendicular. One of them isn't. Rather than trying to mess with two forces, why don't we just take the one and change it? So we change our reference frame. So rather than making y here and x here, what we'll do is this. We're going to make I'm totally eyeballing it. We're going to make...
Oh, that's not right. That's not right.
Oh, stop.
That's like, it's like 85 degrees.
Did you just say that? You goober. Okay. Why even do those? You go all the way. All right. So x and y, right? Shh. So here's what I've got. We're rotating our reference frame. So it's at that angle. Does everyone see that? You see why I'm doing that? Okay. So now I can take my force of gravity, and there is some force that is going this direction. And there's some force that's going this direction. Right? FGY, FGX. Okay? So I'm going to go ahead and I'm going to, oh, come on now. I'm going to move this over here. Do you want to do this or do you want me to do this?
What do you mean?
Where
You
was
want-
the F? Oh, yeah. Is that X on the left side? Okay, yes.
Okay. So I'm going to, so we've got this.
So we're
Oops.
just looking at this like the force of gravity is now coming out like the back end.
Okay, we're going to draw the free body diagram right now. We're going to answer the question. So this is just the object, okay? Let's draw the free body diagram. So I have friction going. Actually, I'm going to. Is it raining again?
Yes.
No, it's really.
It's raining.
No,
It brings
it's
us
Quiet. Guys, quiet. Okay. So I've got my, I'm going to draw this. Listen up. Hey guys, I'm going to draw this way. I'm going to draw it normal. I'm going to rotate it, okay? Here's my FR. Here is my FGX. Here's my F normal. And here is my, oh, that's FGY, excuse me, FGY, right? Here's my FGX. Do you guys see that?
Yes.
Everyone see this? I'm just going to rotate. God darn it.
That makes sense.
So there's my free body diagram. Does everyone see that? Okay. The question is, I know what my normal force is going to be. It's going to be opposite to my FGY, isn't it?
Yep.
Right? But I need to figure out FGY and FGX. Okay, let's look at this blown up. Okay, this angle here is 30. Is that angle theta? Where is this angle in my new? Where's my triangle? Where's my new triangle here?
Right there.
My new triangle. This is important, guys. I need you to see this. My triangle is here. Oops, excuse me. Here,
Hold it down.
here,
That first line was like
and
a perfect
here.
trace.
well, because I have a little thingy to go up and down.
Okay, that's what.
So I can do like this,
But then
or
how
like
come
that.
they introduce,
Because it's only orthogonal.
and
Right.
oh, and in our
Yeah. So here's the triangle. What angle is this? What angle is that? Let's look at this. Let's look at the triangle, okay? If I have it is theta, isn't it? Because if I've got my triangle here, here, right? And here, where this is perpendicular. Okay? And then I have this guy, which is like this. Okay? Everyone see this? That's the two triangles I have, right? Okay? Because it's that way. If this here, come on, dude. If this is theta, and that's 90 degrees, what's this one over here?
That's 90 minus
90 minus theta.
180.
And if this is 90 degrees, and this is 90 minus theta, what's this one here? Theta. Right?
Yeah, okay.
You guys see that? If this is theta, 90 minus theta is theta. Similar triangles. If this is 90 degrees and that's 90 minus theta, that must be theta. So that angle here has to be theta. Okay? But what I want you to be careful is when you draw your triangle, draw it like this, not like this.
Yeah.
You see the difference?
One is
You want that FG, you want what you're going to make a mistake on.
I don't know why I was drawing that way though.
You're gonna do it. I'm promising.
Why?
Because this looks like a real triangle. This looks like the triangle you might want to draw because
that's
you're
not
not
a real life problem.
right.
That was like
The
every
FG, you have to realize that FGX is at an angle here, and you want to see where FGX and FGY are perpendicular, and that creates a triangle like this, not one like this. Because a lot of people will do this, David.
I mean, if I just draw it on the.
But watch, a lot of people. Here's what you're gonna do. A lot of people are gonna do this, and that triangle there.
Ooh.
That's not what you want to do. You don't want to do that. Does that make sense? That's what you don't want to do. You ever see the difference? Because at that point, FGX and FGY are not perpendicular. Follow me?
Yeah.
Okay. So once you've got that, all right, I'm going to erase this. Okay. I'm going to redraw the triangle. Okay, of my FG. So here's my FG, right? Okay, and here's my FG what? What is this? What is this guy representing?
FGY.
FG what? Y. FGY. And then this guy right here is what? FGX. Do you guys see that?
Yeah.
Notice how short FGX is. Notice how short FGX is. FGX is short. Why is it short?
Because.
Think about a vector. What does the arrow represent in the vector?
Oh, because it only changes slice.
Well, let's think about this. Is this a really steep or a really shallow angle?
Pretty shallow.
So how much in this direction is gravity pulling? Not much. That's why it's small.
Oh.
If I raise it up, then the FGY would get smaller, FGX would get bigger. Do you guys see that?
Yeah.
So that's representing the magnitude of the force. That means our gravity is not going to have much force in this direction, right? So if I know that that's theta, okay, then I can say FGX is equal to what? Everyone like this. What's FGX equal to? Give it to me. Wait, give me one. FGX is equal to what? FG, not FGY, FG sine theta, right? FG sine theta. It's opposite. Yeah, it's opposite. Now, normally our x's were cosine, but because it's sort of our triangles flipped around, you have to be careful. So FGX is our sine theta. FGY is what? FG cosine theta. And then the problem is the same problem as you had before. Now you do the sum of the forces. Sum of the forces in the x are equal to what? But what are they? What are they? What are my forces I'm summing up? F friction. And if they're balanced, what's happening? Equals 0. What about the sum of the forces in my y? FGY plus. Where's my FG? Where did it go?
It's FG.
Okay, good. Is everyone clear on this problem? B. And then if I had another, look, if I had another rope, if I had a rope here, pulling, here's my rope, then I'm going to have another force of my rope. Where does that guy go? And the sum of the force of the x, right? The construct that I gave you and that you've been working with is the same for all of this. Okay? Be prepared to do a problem like this.
Like actually like that?
Uh-huh.
Something completely different.
Yeah, did anyone finish your test yesterday? Because I
Yes.
heard that pretty much everyone dropped it.
No. I actually have people did really well on the test.
Did anybody not drop it?
What? Oh no. It's a very no. I looked at them as they were handing in. I saw people's work. They were doing really well.
People did not drop this test.
I don't know.
You haven't graded it yet.
I haven't seriously. I just looked at them as we went through briefly.
I have heard from 7th period that many people just sat there and didn't finish it.
You have to realize you're young, and I get this.
Young and right.
Yeah.
Oh.
What does that mean?
You're impressionable. Okay. Rumors happen. You hear these. You hear one. No. You hear one story and you think it's everybody.
No.
Were you there during that class?
I
Were you
have
there during my class? How do you know they weren't trying to make you feel bad? All right. Shh. Let's move on to the next thing. Guys, be prepared to do this problem. We'll do some more of this. I'm gonna give you a problem set for this. End of this week or next week. So be prepared to do some. Think about this. This shouldn't be anything new. Okay? Shouldn't be anything new. It's just.
So you're like highly
Different
evaluated.
concepts.
Yeah.
Nope. I got stuff to do. All right.
It's just different concepts.
It's the same thing. It's just turned a little bit by now. Turned slightly sideways. Stop with the scrubbing.
Hey, question. Why did you put that on Trip's desk yesterday?
What?
Why did you put that on Trip's desk yesterday?
I just thought it was funny. I just want to stare at it. I had to stare at it. Okay. Shh. Okay. Let's talk about energy. Let's talk about energy. Guys, quiet. Energy. Talk about energy, okay? Energy. So when an object moves, or an object has height, we have energy, okay? We haven't even gotten into work. Oh, I gotta get into work. All right. Let me just do one thing really fast.
Yeah.
Did I miss something? Please transforms. I want to get into and work energy before I get into centrifugal force. Okay. All right. Okay. So let's talk about work. We're going to talk about work and energy. Okay. Work is defined as the amount of energy. Okay. That it takes to do something. Okay. So work is equal to our force times the force that is parallel to our displacement that we're going to actually move. So if I move something, if I take a certain amount of force to move something, it's going to be that force times the parallel displacement to that force. This is going to be my work. An example being, okay, if I take a certain amount of force, okay, I apply that force to an object, and I move it a certain distance, the amount of work is in joules. So if I said newtons times meters ends up being joules. So I say, okay, let's say it's a 10 newtons I apply, and during that 10 newtons I'm able to move that object, okay? I'm going to move that object 5 meters. So the amount of work that is done is 50 joules, okay? Now, if, however, here's the trick, guys. And we're going to get into energy and potential energy and kinetic. If I, however, took and I pulled this direction at an angle, the work that's being done is only f of x times d.
So we would just apply the force of F in the x direction.
Parallel to the distance. Okay? Or displacement. So if I were making an object, I moved it up, and I said, and this is a classic example, right? I've got an object. Because here's the issue, right? The issue is this. Hey, Mr. A, I'm pulling a big object, a big mass, and it's going to be 100 newtons, right? And I'm going to pull it up with a force, okay? I have a force from a cable pulling up from a crane, right? And that's the force of my crane. Here's my force of gravity. Let's say that my force of my crane equals my force of gravity. That means my net force is what? Okay. One of two things is occurring. My object is doing one of two things. What are those two things? Not moving or constant velocity. So it's like I'm lifting up I could be lifting this box up or this weight up at a constant velocity. It has no acceleration. But then, Mr. A, how could you be moving it? Because there's some force going on, right? So it's your force times your displacement. Okay? All right. Okay. If my force is moving, then it's the force times that displacement. Hold on one second. Let me. Okay. Now, I'm doing work on the object, right? Pulling the crane's doing work on the object, but gravity's also doing work on the object, right? In the other direction. So the work's going to balance out. So the net work is going to be ultimately 0, okay? But each one's doing different work. When we talk about, did you guys do potential energy and kinetic energy in middle school?
Yes. It's been like 5 to 4 years.
Okay.
Fifth grade.
Okay. Here's the thing. All right. And I really should have done. I think as I'm going through this year after year, I would also next time I will do energy along with my two-dimensional motion.
We'll do it next time because you're leaving.
I know, but I'm saying.
Sorry,
Stop.
California.
Okay. Okay. Shh. Okay. So, yeah.
Can you explain the physics of this pencil? Like whenever it bends, why does it do that? I've always wondered. Honestly, here,
Okay.
we do this first.
Okay. So I've got. I want you to figure that out.
Well, okay, I get it. It's like gravity.
Well, what's
But
okay?
why is it like what? I don't get it.
All right.
Magnetic field.
B field. But the forces are balanced, right? To have it, the force pushing up is balancing the force of the object going down, right? Okay. Shh. So here's, guys, listen up. Objects, guys, it takes work to get an object up here. I got to take some work to get this object up here, okay? So once I do that, all right, once I put it up, this object is going to have, this object's going to have some energy to it, right? It has the potential to do what? This ball has the potential to do what?
Ball.
Okay, so this ball has what we call potential energy. Potential energy. So potential energy is defined physically as the mass times the force of gravity times its height. Right? Again, or mass times the acceleration of gravity, times height. But look, remember we said that work is force times displacement. What's the unit of force?
Joules.
Newtons. What's the unit of displacement? Meters. What's mg? What's the unit of mg? Mass times acceleration of gravity. What is that?
Oh, force.
Which is a newton. Times an h, which is a meter. So it's all the same thing. Okay? So we have the potential energy. Okay? The other thing we have, so as this thing is here, so we've got a couple things. So right now, let's say we're at a certain height, the ball is a certain mass. Okay? Let's say the mass is 10 kilograms. Let's just, for number's sake, acceleration is negative 10 meters per second squared. And our h is going to be 20 meters, okay? So our potential energy is equal to 10 times 20 times 10, which is 2,000 joules, okay? So when we talk about energy like this, it's the amount of energy that it has, that it can release by falling, okay? So I can ask you, so you could calculate, when I'm at this point, I have so much energy, and let's say after a certain amount of time, I'm going to be a certain height, I'm going to have a different energy, aren't I?
Yeah.
Right? When the ball reaches the bottom,
0.
0. We'll pick up with kinetic tomorrow.
Everything is 0.